Hi everyone! Some of you have asked follow-up questions about the previous lectures. Namely, we considered time-discrete signals, but physical reality is time-continuous. How do we correctly convert time-continuous signals into time-discrete ones? And can we actually go back from the digital to the continuous domain? A second issue is if other LTI systems exist than this one. Well, the answer to these questions are Shannon's sampling theorem and IIR filters. And that is what this lecture is about. Welcome to the Essentials of Signal Processing, lecture number 3. Converting signals from the physical world to the digital requires two steps. First, we need to obtain a finite number of signal values per second or per centimeter, the samples. And second, we have to limit the signal to a finite number of possible signal amplitudes. We're just focusing on the first one here, called sampling. Sampling is the process of recording the signal's amplitude at particular time instances, for instance every ts second, and discarding the rest of the time-continuous signal. The second step effectively rounds the resulting signal samples to a limited number of discrete values, signal amplitudes or pixel values. This rounding process is also called amplitude quantization, and it plays an important role in the efficient storage of digital signals. Quantization determines how many bytes of storage are required for a single signal sample. In this course, we assume that we are using enough storage bytes to effectively ignore amplitude quantization. The sampling in time or space, however, cannot be ignored. In fact, if you sample incorrectly, the time-discrete signal is going to be a very poor or even completely incorrect representation of the original time-continuous signal. So how many samples should we take per second? How many is enough? In other words, what is the minimal sampling rate? To illustrate this, we consider a simple time-continuous cosine signal with frequency of 3000 Hz, shown here. We sample this cosine with a rate of 9000, 6600 and 5100 samples per second. If we look at the time-discrete signals, it is intuitive that for the first and the second one, we can recover or reconstruct the original cosine in this way. For the third one, however, this one is the best bet. And that is not right, because the reconstructed frequency is now clearly lower than what we started from. We can also listen to this effect. Listen carefully to the reconstructed signal, what happens when we lower the sampling frequency from 9000 to 5100 Hz. Obviously, there must be a certain minimum number of samples that we need to take per second for exact reconstruction. And from this example, the intuition is that the minimum requires 2 samples per period of the cosine. And that is precisely what Shannon's sampling theorem says for sampling arbitrary signals. Namely, if we have a time-continuous signal xt with frequencies no higher than fmax, then the signal can be exactly reconstructed from its samples taken at equidistant time instances ts if the sampling frequency 1 over ts is greater than twice the maximum frequency fmax. The minimum sampling frequency is also called the Nyquist rate. In other words, if you know the maximum frequency in the signal, then you also know the correct sampling frequency, namely twice that maximum. I think we can agree that this result deserves to be the signal processing equation of the week. You all know the practical application of Shannon's sampling theorem. We humans cannot hear frequencies higher than 20 kHz. Therefore, it makes sense to sample high-quality digital audio at 44.1 kHz. For visual information under normal circumstances, we cannot see temporal frequencies, those are changes in intensity in time, higher than about 30 Hz. This is why video recording and production and monitors often use a display frequency of at least 50 to 60 Hz. A bit conflicting with this nice theory is that in practice time-continuous signals may not have a maximum frequency or a maximum frequency that we cannot accommodate with our sampling process. If we then use a sampling frequency that is too small, the signal frequencies higher than half of the Nyquist rate cannot be reconstructed. You might think, so what? We just lose these frequencies. But as we saw and heard earlier in the small example, a frequency, or tone in this case, that is higher than half of the Nyquist rate will be reconstructed as a lower tone that did not exist at all in the original signal. This phenomenon of getting back the wrong signal frequencies if you undersample is called folding back aliasing, or just aliasing. Aliasing should be avoided at all costs, as it makes good reconstruction of the original time-continuous signal impossible. For that reason, an anti-alias filter is often applied prior to sampling. This time-continuous filter limits the maximum frequency of the time-continuous signal. For instance, when you take a digital picture, the lens acts as a spatial anti-alias filter prior to the spatial sampling by the CCD inside your camera. It should now be clear to you that a high-quality lens in combination with a low-resolution CCD is not a wise combination, because you will then be violating Shannon's sampling theorem, and typical moire artifacts will appear in the resulting photo, looking like those shown here on the right-hand side. Unfortunately, aliasing cannot always be avoided. The best known example is movies in which the wheels of cars are turning the wrong way. That is what temporal aliasing looks like. Let us do a bit of math using the sampling theorem. Consider the time-continuous cosine signal with a frequency of f Hz or radial frequency omega, shown here. Using the sampling frequency fs, we obtain this time-discrete cosine as a result. Important in this equation is the ratio between the signal frequency f and sampling frequency fs. Due to the sampling theorem, this quantity must be smaller than 0.5. As a consequence, the maximum digital frequency that can exist in time-discrete signals is also 0.5. It is important to realize that this number is not a real frequency, so not half Hertz, but a ratio between the signal frequency and the sampling frequency used. If we look at the digital radial frequency omega, calculated as 2 pi f, we see that it must be smaller than pi. This is something you're going to see back in the coming weeks when I introduce the discrete Fourier transform. Make sure that you understand the concept of digital frequency, namely the fact that it is a ratio, not a real physical frequency, and that you need to know the sampling frequency used in order to convert the time-discrete signal back to the time-continuous domain so that you can listen to it. Shannon's sampling theorem says that we can exactly reconstruct a signal from its samples if we take the correct sampling rate. But how? Well, Shannon also proved that this requires a time-continuous sinc function to be erected at the position of each sample with the proper amplitude, and then add all resulting sinc functions. No system does it in this way, as it's rather impractical. In digital to analog conversion, we often just use simple interpolation between the sample values. This is what DA converters in audio amplifiers do, for example. And in today's display of digital photos and video, we just project the sample values, the pixels, on the screen and let our visual system do the spatial interpolation. With that, we move to the second topic of this week, IIR filters. We have seen this LTI filter before. Its impulse response has only a finite number of non-zero values, namely the n+1 filter coefficients b sub k. For that reason, these filters are also called finite impulse response filters, or FIR. Unsurprisingly, there's also such a thing as infinite impulse response filters, or IIR. An IIR filter has an impulse response Hn with an infinitely large number of non-zero values. We get such IIR filter if we not only use input values xn to compute the output yn, but also use other output values. Of course, these values must have been already calculated, so we can only use previously calculated output values. In other words, y at n-1, at n-2, and so on. In its simplest form, we get this first order IIR filter. The more general form looks like this, where the summation of L runs over values equal to or larger than 1. While in FIR filters we could immediately obtain the impulse response from the filter equation, namely the coefficients b sub k, this is no longer true for IIR filters. In this case, we need to calculate the impulse response by inputting a unit impulse signal at n is 0 and subsequently observe the output. This animation shows the result for a simple first order IIR filter. In this case, we can even write Hn in closed form, But for higher order IIR filters using multiple previously calculated yn values, such elegant closed form is typically no longer achievable. An important observation can be made from this result. Namely, if the value of a1 is larger than 1, the impulse response grows indefinitely. In a sense, the impulse response explodes, and we call such an IIR filter unstable. Unstable IIR filters are useless, as the output no longer depends on the input. For this first order IIR filter, the conditions for stability are easy to find. But for higher order IIR filters, that is much harder, and we consider that out of scope for this course. So yes, there are other forms of LTI filters than FIR. IIR filters are important for audio, for music and for real-time control systems, for instance, in industrial processes or self-driving cars. But for many computer science applications, such as computer vision, machine learning using convolutional neural nets, signal quality improvement and compression, we usually use FIR filters. Summarizing, the learning objectives for this week are: first, you can determine the proper sampling frequency for a given time-continuous signal. Second, you can mathematically derive the time-discrete cosine signal from its time-continuous version and vice versa. Third, you can explain the concept of digital frequency and digital radial frequency and why they are smaller than 0.5 and pi respectively. Fourth, you can calculate the impulse response of a first and second order IIR filter, and finally you can determine if such an IIR filter is stable. We conclude again with two exercises. First, given the description of a time-continuous signal xt, like this sum of two sinusoidal signals, determine the Nyquist rate. And if we sample xt with a sampling frequency of 4/3 times the Nyquist rate, then write down the expression of the sampled signal xn and determine the digital radial frequency. Second, given this IIR filter, determine the first 10 values of its impulse response and compute the output of the filter for the given input signal x of n. Today's lecture concludes the description of signals in the time domain. Next week I will start laying the groundwork for signal processing in the Fourier domain. For that, I expect you to be familiar with complex numbers, polar coordinates and Euler's equation. If you feel insecure, check out the refresher complex numbers on Brightspace. See you again at the next lecture.